So what happens when you put a paper cup above a Bunsen burner? Okay, an empty cup. Well, no surprise, you reach the combustion point of paper, okay, Fahrenheit 451, pretty quickly. Let's see what happens when you put a cup of water over that same Bunsen burner, okay, and you will notice that you don't get the same result. What is the difference in what you observe? Obviously, that paper cup is not reaching the Fahrenheit 451 temperature. Okay, why not? What is the effect of the water in that cup? There you see it boiling. Some strange colored water, I must say. So before we can understand why a paper cup of water held above a 600 plus degree Bunsen burner flame doesn't combust, when we know that paper has a combustion point of about 230 degrees Celsius, okay, before we can understand that, we need to formally introduce the concept of heat. Now, from our last lecture, we now know what temperature measures, right? Okay, it's a measure of the average kinetic energy of the particles that make up an object. Okay, but what about heat? We must be a bit careful here because while we're all familiar with the word heat, okay, we need to make sure that we distinguish heat from a related concept called internal energy, sometimes referred to as thermal energy. So we're going to take a trip back in time to visit an old, outdated, no longer believed in theory, okay, of heat. And if you ask, why would we do this? Well, very often it becomes difficult to learn new physics because we have very defined theories based upon our own observations and experiences interacting in the world. And so some of these ideas in the caloric theory are certainly consistent with what we observe in the everyday world. Okay, and there's obviously a reason why they came up with it. I mean, it was based upon common experience and observations that a lot of people had. So it's worth looking at some of these beliefs that many of us may hold, which are no longer considered scientifically valid. So up until about 150 years ago, okay, it was the caloric theory that was used to explain the concept of heat. And the theory went something like this, okay? Heat was thought to be an invisible fluid called caloric. And the idea being that an object possessed a certain amount of caloric, and when an object had caloric added to it, okay, had heat added to it, well, then its temperature would increase. When an object lost caloric for whatever reason, okay, the temperature of the object would decrease. So the temperature of an object, okay, was directly related to the amount of caloric that the object possessed. And it was thought that when an object is subdivided, okay, like in the case of cutting, for example, okay, the caloric is being released. And this could explain the decrease in temperature of the object itself, but also nicely explain the increase in temperature witnessed in the surroundings. So even today, we still use the term heat flow as if, okay, heat was some sort of fluid. As so often happens in science, an observation or discovery is made that is inconsistent with the current model, okay, the current theory. This is exactly what happened with the caloric theory in the mid-1800s. Okay, a fellow by the name of Benjamin Thompson, okay, more commonly known to society as Count Rumford, made some observations in the process of boring out cannons. Now, when you think about how cannons were made back then, large cylinders of solid iron were bored out using drills. I mean, drill bits, very often turned by teams of horses. And in the process of boring out these solid cylinders of iron, water was used to cool the cutting instruments, okay, but eventually these cutting instruments would get too dull to actually cut the metal, Okay, and what Count Rumford noticed is that even when the instruments got so dull they could no longer subdivide the metal, okay, the temperature of the water used in the cooling process still continued to increase. And he noticed that this process could take place indefinitely, okay, meaning that there was really no limit to how much water could get heated. Well, think about what we said on the previous slide about the caloric theory, that if caloric is being released by an object, there should be a finite amount of caloric that is being released. Eventually, okay, the object should run out of caloric. And secondly, that only if an object was actually subdivided would it actually be able to release caloric. So here, we can state these questions raised by these observations that of Count Rumford that contradicted the caloric theory. First of all, how could caloric be released when the dull instruments could no longer subdivide matter? Okay, and secondly, if caloric was a fluid, it should exist in a finite amount, and eventually a sample of matter should run out of it. Okay, so how could heat be generated indefinitely, okay, during the cannon boring process? So you can see how these problems, okay, like very often happens in science, okay, leads to a new theory, okay, which can explain them. So our modern definition or modern interpretation of heat, which is based on kinetic molecular theory, goes something like this. Okay, heat, and we'll use the symbol Q to represent heat. Heat is a transfer of energy, okay, from an object at a higher temperature to an object at a lower temperature, okay, caused or due to a temperature difference between these two objects. So it's really important to note here that heat is not energy, okay, but is rather a transfer of energy. So in the same way that work is not energy, but is rather a transfer of energy due to mechanical means or forces, the same can be said about heat. Heat is not energy, but is rather a transfer of energy that happens for a different reason than work. Okay, it's the transfer of energy that happens because of a temperature difference. Okay, this is something we'll talk in greater detail about when we talk about the first law of thermodynamics. So when it comes to units to measure heat, we have the problem of history, okay, as we do very often with other physical quantities. And that is that although the definition of heat has evolved throughout the ages, okay, we see that we no longer believe in the caloric theory today, but the kinetic molecular theory gives us an interpretation of heat. Okay, although the theories have evolved, we're still stuck. We still, okay, hold steadfast to some of these old units that were introduced a long time ago. So we have to at least be familiar with them. Now, the old SI unit, okay, was the calorie. And this, as you can see, was part of the caloric theory. So, and we still see this unit very often, so you do need to be familiar with it. The calorie symbolized CAL, okay, by definition is the amount of heat that is required to raise the temperature of 1 gram of water by 1 degree Celsius, technically from 14.5 degrees Celsius to 15.5 degrees Celsius. Now, why this definition is used to define the calorie is going to become a lot clearer when we talk about the idea of specific heat capacity. A related unit, the kilocalorie or kcal, or to make things really confusing, just a calorie with a capital C, okay, is 1,000 calories. It's important to note here that when you talk about food calories, when you look at the back of a food package and they, tell you how many calories this item has for a typical, let's say 2,400 calorie a day diet, trust me, you would die very quickly if you were only eating or ingesting 2,400 calories a day. You're really ingesting, okay, a typical diet of, okay, 2,400 capital calories or kcals. So we're really ingesting more like, okay, 2,400,000 small calories a day. So I have no idea why that's the case. It is confusing, but make a mental note of it. Okay, a food calorie is really a kilocalorie. Of course, our modern unit to measure heat, if heat is a transfer of energy, then you would expect it to have energy units. So of course we know that joules is our SI unit that we use to measure energy. And okay, you know a joule is, okay, kilogram meter squared per second squared. The British unit we still come across. If you're going to buy a water heater, for example, you might see, okay, a rating in BTUs or British thermal units. And a British thermal unit is the amount of heat required to raise the temperature of 1 pound of water, okay, by 1 degree Fahrenheit, from 63 degrees Fahrenheit to 64 degrees Fahrenheit. So you see here that our definition of the BTU looks pretty similar to the concept of the calorie. Okay, and we'll see why, as I said, once we understand the meaning of specific heat capacity. Okay, that will give us an understanding for how much heat gets transferred to or from an object. Now, James Prescott Joule, okay, a bust who you see on your screen here, okay, and a scientist that we all know and love, he, while on his honeymoon, okay, had always wanted to show that when water fell through a certain distance, 778 feet to be exact, that the temperature of the water would rise by 1 degree Fahrenheit, okay, for such a fall height. So James Joule had this opportunity on his honeymoon. He married a lady by the name of Amelia Grimes, and on his honeymoon he visited a waterfall and conducted a series of experiments. He measured the temperature of the water at the top of the falls, then measured the temperature again at the bottom of the falls, because he suspected that the work done, okay, by the falling water would increase its temperature. And that is exactly what he found out. Okay, so what a truly romantic thing to do on your honeymoon. Okay, be sure to take good notes, everybody. Okay, especially for those of you who are not yet married. But James Joule does get credited with discovering this relationship, okay, between work and heat, and this is what we call the mechanical equivalent of heat. And he discovered this exact relationship through his famous paddle wheel experiment, okay, that looks something like this. And you can see here we have a chamber with a paddle wheel. That chamber is filled with water, and these weights can be cranked up to a certain height, okay, by turning the crank, and in so doing, a certain amount of work would be done by the paddle wheel on the water. And you can see the thermometer there. That amount of work could would increase the temperature of the water, which could be measured. Certainly when those weights then fall, their loss of gravitational potential energy will get converted into the thermal energy, okay, get transferred to the water in the form of heat, and again raises temperature. So with enough of these terms, Joule is able to very accurately figure out what that correlation was between, okay, the energy added to the water and the change in temperature of the water, okay, the amount of heat that was transferred. This is what we call the mechanical equivalent of heat. So Joule discovered that doing a given amount of work on an object always produced a certain amount of heat. What is that amount of heat? It's what we call the mechanical equivalent of heat. And it turns out that, okay, 4.186 joules of work is equivalent to 1 calorie of heat. So this mechanical equivalent of heat can really be thought of as nothing more than a conversion factor, okay, between work and heat. And we'll take a look at a problem, okay, one that's you might find interesting, okay, that will make use of this mechanical equivalent of heat. So it turns out that lovemaking requires between 500 and 1500 kilojoules of work, depending on fervor, of course. So we're asked to find how many food calories would a very fervid 3 rounds per week person lose in a year if no additional food were eaten to match his or her sexual appetite. So treating this as a converting units problem, okay, we will start here. Notice here that we have, okay, this is a very fervid individual we're talking about here. Okay, obviously someone much younger than myself. So we'll go with the 1500 kilojoules, okay, per round. And it times 3 rounds per week, okay, will give us how many kilojoules per week. And if we want to convert this, since we're asked to find out, okay, how many food calories would be lost the entire year, we'll convert weeks into years, okay, by multiplying by 52 weeks to the year. And now we get to use our mechanical equivalent of heat. Okay, so if 4.18 joules is equivalent to 1 small calorie, we can say that 4.18 kilojoules is equivalent to 1 kilocalorie or food calorie. So this turns out to be 56,000 kcals per year. So the more interesting question that we all want to know, I'm sure, is, you know, how much weight would such a person lose in a year, okay, given that the energy content of 1 gram of fat is 9.6 kilocalories. So, okay, given this form of exercise, how much weight could be lost in a year? Assuming, of course, that you don't, you know how that goes. If you get hungry, you're going to eat more to make up for it. That's one of the problems with, you know, using activity, being very active to actually lose weight, is that you tend to be, you know, hungrier when you're getting more exercise. But assuming that, you know, we're just going to do the calculation here. So again, a conversion factor. So we'll take the 56,000 kcals per year. Okay, we will turn that into a mass in grams, noting that 1 gram of fat is equivalent to 9.6 kcals. So this is 5,800 grams or 5.8 kilograms per year. When you convert that to pounds, about 13 pounds per year. So like I say, it sounds like a lot. Okay, and you know, assuming that food was not, additional food was not eaten, okay, to, you know, replace those calories burned, okay, then about 13 pounds per year could be lost, okay, given this activity. So we say that heat is a transfer of energy, okay, from one object to another due to a temperature difference. But how do we actually measure the energy of the system itself? Okay, well, a related quantity, okay, but distinctly different, is what we call internal energy. And we will use the symbolism capital E with the subscript INT to represent the internal energy of a system. So what do we mean by the internal energy of a system? We're talking about the sum total, that is all forms of microscopic energy. That means the total microscopic kinetic energy, okay, due to all forms of kinetic energy, as well as all forms of microscopic potential energy associated with that system. Now you'll notice here this condition that says when viewed from the reference frame at rest with respect to the center of mass of the system. Well, think about this. You know that when we talk about the kinetic energy of an object, okay, it depends upon the speed of the object. Well, you know that the speed of an object, okay, is going to be dependent upon the reference frame from which it is measured. In one reference frame, an object might not have speed, okay, but another reference frame it would. So clearly the reference frame will affect, okay, your measure of the kinetic energy of the object. So that's why we add in this condition, okay, when viewed from a reference frame at rest with respect to the center of mass of the system. We'll talk more about that in the next slide. So when we think about the microscopic energy, we're talking about the energy associated with the particles that make up the object. Now, I use the word particles very generally. A particle could represent an atom. if your system could consist of atoms, let's say noble gas atoms, okay, where these atoms will not combine with other atoms, okay, or your system could consist of molecules where you do have atoms that combine with other atoms to form molecules, or your system could consist even of ions. So we use the word particle very loosely. So what are these specific forms of microscopic energy, okay, whether kinetic, okay, or potential? Let's take a look. So when we talk about the microscopic energy of the system, we could be referring to the vibrational kinetic energy of the system. Now you know that solids, okay, which do not have a whole lot of motional freedom, most of their kinetic energy, their motional energy, is in the form of vibrational kinetic energy, as this simulation shows. Solids do not have a lot of rotational or translational freedom. Okay, but if we talk about liquids, okay, liquids, the particles have the ability not only to vibrate, okay, with respect to each other, but also to rotate around each other, and that's what gives liquids this ability to flow. So we have to look at the rotational kinetic energy as well. When we talk about gases, we know that gases have the ability to, gas particles can completely move apart from each other. They can move from one side of the container to the other. This is translational kinetic energy. So we have to look at that form of kinetic energy as well. When it comes to potential energy, okay, we have to look at the potential energy due to the intra-particle bonds as well as the inter-particle bonds. When I talk about intra-particle bonds, these are bonds, okay, within a given particle. So this would only apply to cases where you have, let's say, molecules that consist of 2 or more atoms. And you can see here that this is a given particle on your screen, but which consists of a collection of 3 different atoms. And you can see here, if this was a water molecule, that there is a bond between each hydrogen atom and the oxygen atom. And there is a bond energy, there's potential energy associated within that bond. That is an intra, which means, okay, between atoms here, an intra-particle bond. Okay, not to be confused with an interparticle bond. This would be bonds between particles. So what you're seeing illustrated here are 2 particles, and if I can get my laser pointer here, you'll see that these 2 particles are being joined. Okay, there is a bond between these 2 particles right here, which possesses potential energy. So that is an interparticle bond. So in this slide, we'll take a closer look at the difference between the macroscopic energy of the system and the microscopic energy of the system. So we'll consider a simple system here. If I was giving this lecture face-to-face, I would do this in front of you, but okay, here we'll just use a picture. Consider we have 2 tennis balls, identical in all respects, except that one is on the table, the other is on the floor. Okay, you see that, really the only difference, okay, between these 2 balls is that one exists at a greater height, okay, relative to the center of the earth. So which of these tennis balls has the greater internal energy? Okay, well, clearly you see that the one on the table has a greater macroscopic energy, right? Because it has more gravitational potential energy than the ball on the floor. Okay, but that's not what we're interested in. When we're interested in microscopic forms of energy, okay, assuming that the particles within each tennis ball have the same amount of microscopic kinetic energy, they're moving at, okay, the same speeds, they have the same level of vibrational, rotational, and translational kinetic energy, as well as, okay, both forms of intra-particle and interparticle potential energies. So here we can say that both of these tennis balls have the same microscopic energy, although they clearly have different amounts of macroscopic energy because the ball on the table has a greater macroscopic potential energy. Okay, let's assume now that one ball rolls off the table here. Okay, how does its internal energy compare to the ball on the ground while it's falling? Well, once again, okay, we can say that the ball that is falling has a greater macroscopic kinetic energy. All of those particles, in addition to their microscopic random vibrational, rotational, translational motions within the ball, okay, in addition to that, now all those particles are moving downwards with the kinetic energy, the macroscopic kinetic energy of the ball. But you see that that is a macroscopic form of energy. Okay, and that is why we add this condition when viewed from a reference frame at rest relative to the center of mass of the system. So you see that even while that tennis ball is falling, okay, and all those particles have a macroscopic kinetic energy when measured from a reference frame, okay, of the floor, okay, when measured from a reference frame of the center of mass of the moving ball, okay, now you can see that the moving ball, those particles have the same kinetic energy when measured from that reference frame as the ball on the ground. Okay, so although the falling ball has a greater amount of macroscopic kinetic energy, its microscopic kinetic energy will be the same as the one on the ground, assuming that we neglect air friction in the particle. Okay, making that assumption, then you can see the difference between macroscopic kinetic energy and forms of microscopic kinetic energy. So now that we've formally defined the concept of internal energy in this video, as well as the concept of heat, let's make a comparison between these two quantities, as well as the concept of temperature, which we defined according to kinetic molecular theory in our previous lecture. So just in one slide, let's just kind of review the differences between these three quantities and their definition. So when we talk about the internal energy of an object, of a system, okay, we're talking about the total microscopic energy of all the particles in the object. And okay, we just said there's many forms of microscopic energy, both microscopic kinetic energy in the form of vibrational, rotational, and translational kinetic energy, as well as the two forms of microscopic potential energy. Temperature, you recall, is a measure of the average translational kinetic energy of the individual particles in an object. So this is a little bit of a restriction here. So technically, when we talk about temperature, we're talking about, okay, the translational kinetic energy of the particles only. Okay, we're ignoring the rotational and vibrational forms of kinetic energy. When we talk about heat, we're talking about not energy itself, but the transfer of energy between objects due to a temperature difference. All right, so in this slide, we will take a look at a specific example that will illustrate the differences between these three related yet distinctly different quantities. That is internal energy, okay, versus heat versus temperature. And in order to do so, we will take a look at two systems and take a look at each of these quantities, okay, in each of these two systems. So these two systems, the mug of hot coffee versus the backyard swimming pool. So if I were to ask which of these two objects, the hot cup of coffee or the swimming pool, has the greater or higher temperature and why, well, certainly you don't need to take a course in physics to know which of these objects is at the higher temperature. Okay, you have enough life experience to tell you that. Okay, it's going to be the hot cup of coffee. But to answer why, you would need to know the meaning of temperature. We would say that on average, the particles in the coffee, really the molecules of water in the coffee, have a greater kinetic energy on average than those water molecules in the swimming pool. And therefore, the hot cup of coffee is at a higher temperature. If I were then to ask you which of these two objects has the greater internal energy and why, okay, whereas temperature is a measure of the average kinetic energy of the particles that make up an object, internal energy is a measure of the total microscopic energy of the particles that make an object. So here, even though the particles of water in the swimming pool are not moving quite as fast on average as those in the hot cup of coffee, okay, there are so many more particles in the swimming pool that even though they are moving slower, okay, when you look at the sum total, the total energy of all the particles, okay, the swimming pool is going to have a lot more internal energy than the cup of coffee. And finally, if we were to say which of these objects, which of these systems would heat your finger more and why, well, again, you, from your life experience, you know that you can stick your finger in a swimming pool and it's not going to okay, heat your finger much, okay, but do it in the hot cup of coffee and it's certainly going to heat your finger a lot more. Why? Well, because when we talk about heat, we're now talking about a transfer of energy. And it turns out that the object that is at the higher temperature, okay, will be able to transfer more energy to your finger, okay, before thermal equilibrium is reached.
Now, this next concept we'll introduce in this unit is a concept that we call specific heat capacity. And it turns out that specific heat capacity is one of three factors that will affect temperature change when heat is being added or removed from an object. So rather than simply tell you what these factors are, I would like to play a guessing game and see if you can use your life experience to make some predictions about what these factors are. So here's the puzzle or the guessing game, the challenge that I propose to you. I'm thinking of some unknown object. Sounds sort of like 20 questions, right? Now, suppose you add heat to this object. Can you think of three properties, that is, three factors, that will affect how much the temperature of this object will change? And then once you've identified these three factors, how are each of these factors related to the temperature change? In other words, is there a direct relationship or an inverse relationship? So you may want to pause the presentation here and think about these, see if you can come up with any of these three properties. Alright, so let's see how good you were at actually solving this puzzle. So, of these three factors, the first factor that we'll talk about is really the size of the object. Now, there's lots of ways to measure size, but one of the ways to do this is in terms of the mass of the object. And hopefully you would agree that if you're going to add heat to an object, that the amount that object's temperature will change will depend upon its size. Imagine trying to heat a sample of water on your stove. Certainly you know that if you want to heat a small amount of room temperature water up to boiling, that its temperature will change, okay, much more for a given amount of heat than if you're trying to heat up a large amount of water. So in other words, adding a certain amount of heat to a small amount of water will change its temperature much more than adding the same amount of heat to a large volume of water. So that tells us then that there is an inverse relationship between the size of the object and its temperature change. Okay, that small objects will experience much greater temperature changes. Now, a second factor, and this one may be so obvious that you overlooked it, is the amount of heat added. Obviously, if you add a small amount of heat to an object, its temperature will not change nearly as much as if you add a large amount of heat. This tells us that there's a direct relationship between the amount of heat added and the temperature change. Adding more heat causes bigger changes in temperature. Now, this third and final factor or property is what we call specific heat capacity. And we'll talk in greater detail about this in the next slide. But for now, realize that the specific heat capacity of a substance is dependent upon what the substance is made out of, upon the type of substance. And a good way to think about specific heat capacity is to think about it as a measure of thermal inertia. Now we know that inertia is a measure of a resistance to change. And thermal inertia we can think of as a resistance to changes in temperature. So if a substance has a high specific heat capacity, like water, let's say, that means that it has a lot of thermal inertia, that it has a great resistance to having its temperature changed. A substance with a much smaller specific heat capacity will change its temperature much more readily. And because of this definition, it turns out that there's an inverse relationship between specific heat capacity and temperature change. That is, substances with high specific heat capacities don't change their temperature very much when heat is added.
So in this slide, let's summarize the results from this very fun game we played on the previous slide. And in conclusion, we can say these three factors, okay, that affect the temperature change of an object, okay, we can express it like this. We can say that, okay, the temperature change of the object is directly proportional to the amount of heat added, okay. Add more heat, get a bigger temperature change. It is inversely proportional to the mass of the object, okay. The greater the mass of the object, the smaller the temperature change. And the way we define this quantity we call specific heat capacity, we can say there's also an inverse relationship. Okay, that an object with a large specific heat capacity would experience a smaller temperature change, okay, for a given amount of heat added. We can express, okay, these relationships in what I call the sing-along version of this relationship. Let's get our singers here. We can say that Q is exactly equal to MC delta T. Has a nice ring to it, doesn't it? And the way we define this quantity called specific heat capacity, it really becomes our proportionality constant, okay, in this relationship. And it turns out, like we said in the prior slide, that the specific heat capacity of a substance is substance dependent. Okay, it depends on the actual type of substance that we're talking about. All right, so what exactly do we mean by the specific heat capacity of a substance? Let's formally define it. The specific heat capacity, symbolized with a little c, is the amount of energy required to raise a unit mass of a substance. Okay, we usually use either a gram or a kilogram by 1 degree Celsius. Okay, so how much energy is required to raise a unit mass of a substance, to raise 1 gram of a substance by 1 degree Celsius? And we said that different substances, okay, require more energy, okay, to bring about a given temperature change. So we can think of the specific heat capacity of a substance as really being a measure of the thermal inertia of a substance. Remember that if we think of inertia as a resistance to a change, okay, the way we talked about inertia when we talked about mechanics, we said it was a resistance to a change in a state of motion, that mass was a measure of inertia. Okay, the more mass an object had, the more it resisted having its state of motion changed. In the same way here, we can say that the higher the specific heat capacity of a given substance, the more resistance it has to having its temperature changed. Okay, and just like you know in the case of the inertia we talked about in mechanics, you can change the state of motion of an object, but an object with greater inertia requires a greater force to do so. In the same way here, we can say that a substance with a higher specific heat capacity would require more heat added to it, okay, more energy transferred to it in order to change its temperature by a given amount, like 1 degree Celsius. So I think this is a good way to think about it. Think of specific heat capacity is a measure of thermal insensitivity, okay, or thermal inertia. When it comes to units, okay, when we take our Q equals MC delta T sing-song equation here and solve it for specific heat capacity, we see that, okay, Q, heat, is going to be measured in joules, okay, mass either in grams or kilograms, and temperature in degrees Celsius. So we can, our most common units for specific heat capacity are joules per gram degrees Celsius or joules per kilogram degrees Celsius. So in this slide, we'll take a look at the specific heat capacities of some common substances at 25 degrees Celsius. And what you should note here, okay, if you take a look at some of these values, is that water over here has a very high number compared to, let's say, these metals, gold and lead, down here at the bottom. And if we take a look at the meaning, okay, what's the significance of that? Well, this would tell us that for water, it takes 4,186 joules to raise 1 kilogram of water by 1 degree Celsius, whereas when we look at gold, it takes only 129 joules, okay, to raise the temperature of 1 kilogram of gold by 1 degree Celsius. So you can see here that water is kind of special. Okay, water is very thermally insensitive. It has a high thermal inertia. It takes a lot of energy added to be able to raise its temperature, okay, by 1 degree Celsius. And let me put that on the slide here. Water has a very high specific heat capacity, and we can say that in general, metals tend to have low, okay, specific heat capacities. This gives water some very unique properties, okay, and important properties that we'll take a look at in the next slide. All right, so in this slide, we will take a look at some conceptual examples, okay, involving specific heat capacity, in particular, taking a look at the particularly high specific heat capacity of water. So in the first example, we ask, why is the climate so moderate for coastal regions of California? Why is it that California real estate is so much more expensive in the coastal climates than it is here inland in the Central Valley? Well, believe it or not, it all has to do with the specific heat capacity of water. The high specific heat capacity of water allows the ocean to absorb a great deal of thermal energy from the atmosphere, okay, from the sun in the summertime, without raising its temperature too much. So think about it. The sun beats down on the ocean absorbs that energy, and it doesn't raise its temperature very much. That keeps the surrounding atmosphere and land quite cool. When that same sun beats down on the inland region of the Central Valley, okay, unlike water, the temperature of the land raises quite a bit. And since that's in contact with the atmosphere, it raises the air temperature a lot too. So that's what happens in the summertime. But think about it. That ocean, that huge body of water, has behaved as this huge storehouse, this huge reservoir of energy, absorbing the energy from the sun in the summer. But then in the wintertime, when the air temperature, okay, drops below the ocean temperature, now all that stored energy can get released back into the environment, keeping the air temperatures much warmer than they would normally be. Okay, here in Modesto in the Central Valley, we don't have that advantage. Okay, the land has not stored nearly as much energy, okay, during the summertime, okay, to be able to release it in the wintertime to keep the air temperature warmer. Okay, so high specific heat capacity of water has everything to do with real estate prices in California. This next example, I thought we would get away from that large singing purple dinosaur, but I guess not yet. So why is it that when eating a piece of pizza, you're more likely to get your palate burned by the cheese on the pizza than the crust? Okay, when both the cheese and the crust are at the same temperature. Well, once again, it has everything to do with the high specific heat capacity of water. Both the cheese and the crust are at the same temperature, that's true, but the cheese has a much higher specific heat capacity than the crust because of the water and oil in it. So when that pizza is in the oven, it's absorbing energy to reach its final temperature, but the cheese portion of the pizza has absorbed a whole lot more energy than the crust because of the higher specific heat capacity. Now when you take it out of the oven and you put it in your mouth, which is at a lower temperature than the pizza, for exactly the same reason as the water in the ocean behaves as this huge storehouse of energy that can now release that energy to the atmosphere, in the same way the cheese on the pizza has behaved as this reservoir of energy and can now start releasing it to your mouth with the possibility of burning your palate. And finally, why is it that water is such an effective coolant in radiators of automobile engines? Well, if you think about what is the purpose of the radiator, it is to be able to get rid of heat so that your engine, its temperature does not get high enough to actually melt the metal that it consists of. So in the process of combusting the fuel, a lot of heat gets released into that engine, and the water behaves as a coolant. It absorbs that heat from your engine. Because of the high specific capacity of water, the high thermal insensitivity, that means that it can absorb a whole lot of water without raising its temperature too much. You certainly don't want to get the water in your engine to boil. So water can absorb a lot more energy before reaching that boiling temperature than many other substances can because of its thermal insensitivity. So that makes water an effective coolant. It absorbs the energy so that your engine temperature, the temperature of your engine, never gets high enough to actually cause the breakdown of the materials that it's made out of. So finally, we'll talk about this process that we call calorimetry. So what is it? Calorimetry is the process in which specific heat capacities and energy changes associated with physical or chemical processes can be measured by placing objects in thermal contact. And calorimetry, these objects are placed in thermal contact in what we call a calorimeter, which is nothing more than a thermally insulated container where we allow the calorimetric process to take place. Turns out there's two types of calorimeters. There's the cheap type that we call the coffee cup calorimeter, which is really nothing more than a coffee cup. Believe it or not, a polystyrene cup is a good thermal insulator. And with this type of calorimeter, we have the contents inside which are exposed to the atmosphere. So whatever process is taking place inside of there, whether it's a chemical or physical change, it's taking place at constant pressure because, like I said, it's exposed to the atmosphere. Certainly the volume of the contents are allowed to change in this process. Let's compare that to what we call the bomb calorimeter, certainly a more sophisticated type of calorimeter, where we have a closed thermally insulated container, where the volume is kept constant. So the process takes place inside, at a constant volume, but you can clearly imagine that for the energy changes taking place, if there is an increase in energy, due to the process, and an increase in temperature, there's also going to be an increase in pressure. So the pressure would be a quantity that would change in this type of calorimeter. So calorimetric theory is based entirely on the law of conservation of energy, the conservation of energy principle. So when it comes to problem solving, if you want to find, for example, the specific heat capacity of a particular substance, or you want to find the temperature change of a particular substance using a calorimetric process, then we say that when two objects at different temperatures are placed in thermal contact, the heat that will be lost by the hot object must be exactly equal okay, in magnitude to the heat that is gained by the cold object. So you see where the law of conservation of energy comes in. Okay, that we use the symbol capital Q for heat, so Q lost by the hot object, okay, well, we will say is equal and opposite to the heat gained by the cold object, because when we define a temperature change, we typically define it to be the final temperature minus the initial temperature. So the object that loses heat will end up at a lower temperature than it starts out with and have a negative temperature change, whereas the object that gains heat, okay, the colder object to start out with, will end up at a higher temperature than it starts out at, in which case it will have a positive value for temperature change. So that's where we need the negative sign here. We can write it like this if we want. We can say that the heat lost by the hot object plus the heat gained by the cold object, okay, must equal 0. It's a statement of energy conservation. And using, okay, the sing-song version here for, okay, how we determine how much heat gets transferred to or from an object, Q equals mc delta T. I'll use the subscripts H for hot and C for cold. Okay, so the hot object loses heat, so, okay, you know, mass of the hot object times the specific heat capacity of that hot object times its change in temperature plus the same for the cold object must equal 0. Okay, and we can, I'm just going to write, when it comes to the temperature change here, when we place objects in thermal contact, they will both end up at the same final temperature. Remember, that's what thermal equilibrium is all about. Okay, heat will flow from the high temperature object to the low temperature object until both are in thermal equilibrium, until both end up at the same temperature. So you see here that the final temperature, okay, here of the hot object and the final temperature of the cold object will be the same, even though their starting temperatures, the initial temperature of the hot object and the initial temperature of the cold object, will be different.
Now, in this next example, we're going to use calorimetry theory to determine the composition of a coin. So the problem goes something like this. It says that an ancient coin is unearthed from a construction site. To determine its composition, a calorimetry experiment is performed. The coin, having a mass of 27.2 grams, is slowly heated in a calorimeter. After adding 123 joules of heat to the coin, its temperature rises 35.2 degrees Celsius. Assuming the coin is a pure substance, determine what it is likely made of. Now, we can perform a calorimetry experiment, and if we could determine the specific heat capacity of that coin, knowing that it's a pure substance, we could then look up our value in a table and try to match that and try to find out what substance it's composed of. So we're going to start by identifying what information we're given in the problem and what information is needed, what information we're trying to find. And here notice that we're given the mass of the coin. In this case, unlike the last problem, we're actually given the amount of heat added in this calorimetry experiment. And once again, we're told what the change in temperature of the coin is after the heat is added to it. In this problem, we're trying to find the specific heat capacity. The specific heat capacity of a pure substance is unique, and the table will show you that if you can find the value for C, you can identify what the substance is made out of. Just like density, the specific heat capacity then becomes an intensive property of matter. So, knowing what we're given and what we're trying to find, we can use our equation, Q equals mc delta T. We need to find C, so let's solve it for C. Okay, and when we plug in the numbers, the 123 joules is the amount of heat that's added to the coin. The mass of the coin, 27.2 grams, and the change in temperature, 35.2 degrees Celsius. When we do the number crunching, we come up with this value of about 0.128 joules per gram degree Celsius. Okay, the next thing we want to do is we want to go to our table and we want to compare values. Let's see what substance has a specific heat capacity as close as possible to 0.128 joules per gram degree Celsius.
And when we look at that table, we see, aha, gold, okay, is very, very close, having a value of about 0.129 joules per gram degree Celsius. So although this doesn't prove beyond a definitive doubt, it does tell us that this coin is very likely composed of gold.
So in this example, we're going to determine how many calories are in a donut, and you'll see how calorimetry can be used to determining these caloric values that you find on the back of food packages. When you look at the back of a food package, do you ever wonder where those values come from when it tells you how many calories are in a serving of the type of food you're eating? Okay, well, it's done by performing a calorimetry experiment using a bomb calorimeter. So the data given in this problem, a donut is dehydrated, so the water is taken out. It's then burned in a bomb calorimeter so that all the thermal energy released from the burning donut effectively heats up the water. We're told here that 2.75 liters of water is heated from room temperature, okay, about 20 degrees Celsius in this case, to 95 degrees Celsius. And from that information, we want to determine how many food calories are contained within that donut. So we need to remember the whole basis of calorimetry is we're saying that the amount of energy that was in that donut, left the donut in the form of heat and entered the water, in the form of heat. So the energy lost by the donut was exactly equal to the energy gained by the water in the calorimeter. This is the basis of calorimetry. So we need to start by figuring out the mass of the water that was heated. Notice here that we're given the volume of water, not the mass. So if we want to use Q equals mc delta T, we need to find the mass of water heated. So we will convert the volume of 2.75 liters, using the density of water being about 1 gram per milliliter and converting liters to milliliters. We find out that we have 2,750 grams of water being heated. We can now find the change in temperature of the water by subtracting, right? So the water in the calorimeter starts out at room temperature of 20 degrees Celsius, ends at 95 degrees Celsius. That corresponds to a 75 degrees Celsius change. So once we know the specific heat capacity of water, we are now in a position to figure out how much heat got transferred to it. So we're going to multiply the mass times specific heat capacity of water, 4.18 joules per gram degree Celsius, times the temperature change of the water. This tells us that 862,000 joules of energy, got added to the water in the form of heat. Now, if we want to convert this to food calories, using the mechanical equivalent of heat, we know that 4,180 joules is equivalent to 1,000 calories, or 1 food calorie, or large calorie. Using that conversion, we find out that this was a 206 calorie donut. Not bad for a donut. It must have been a small donut. If not, I got to get me some of those. So the last example we'll take a look at in this video also involves calorimetry. This is a slightly more complicated example. And I'll say that I would normally do this in front of students in a face-to-face format, but given the fact that we're in a remote setting, I won't be able to collect the data in real time. But we will use our friendly lab equipment here to be able to help us do something rather interesting, which is to estimate the temperature of a Bunsen burner flame. Now, you can't just go stick in a typical thermometer in the flame of a Bunsen burner, because it will ruin the thermometer. The thermometer is not designed to withstand a temperature like that. So we will use a calorimetry experiment. We will use the law of conservation of energy to be able to safely measure the temperature of that Bunsen burner flame. So let's take a look at the procedure with the help of some friendly lab equipment, starting with our electronic balance. What we're going to do is we are going to measure the mass, of some water in our calorimeter. We can use the tare button, so the balance will tell us exactly what that mass is. Okay, and I will tell you what that mass is on the next slide when we talk about all the data. So we know the mass of the water in our calorimeter. Okay, next we will, with the help of Theo the thermometer, we will measure the temperature of that room temperature water in the calorimeter. Notice that Theo is smiling there because the temperature of the water is just room temperature and he's taking a nice bath, okay, nice and comfortable. Next, we're going to use the ball and ring apparatus. We're going to unscrew the ball, okay, which is made of copper, and mass the copper ball on our balance. So we'll know the mass of the copper ball, okay, which we are eventually going to insert into the calorimeter cup. Once we've done that, we're now ready to start the heating process. There is Betty Burner. Notice she is all warmed up and ready. She's got a nice blue flame. And we are going to now stick the ball and ring apparatus, the copper ball, in the blue flame, and we will leave it there long enough until thermal equilibrium is established between the ball and the flame. So after some time, that ball is going to glow red, and we can assume that the temperature of the copper ball will be exactly equal to the temperature of that Bunsen burner flame. So we will remove the ball and ring. We will quickly insert the copper ball into the calorimeter cup. Okay, stirring occasionally, we will note that the temperature is going to increase, and we will record the peak temperature, okay, of the mixture, that is the water with the copper ball inserted. So let's do that. Okay, let's quickly insert the copper ball into the calorimeter cup. Temperature's rising, and you'll notice that Theo, okay, is looking pretty hot there. And like I said, we will record Theo's peak temperature, and we will write that on the next slide. So in this slide, we will record the data, okay, that we took from our experiment, okay, in the previous slide. So let's take a look here. We have our hot object, okay, our high temperature object, which starts out, okay, being the ball. And our cold object will be the water that's in our calorimeter. We're using our coffee cup calorimeter to be exact. And these quantities on the left, okay, the mass, the specific heat capacity, the initial temperature, and the final or equilibrium temperature, these are the quantities that we need to find in order to solve this problem. So, mass in grams, the copper ball had a mass of 78.3 grams, and the mass of water in the calorimeter was 122.1 grams. Specific heat capacity of copper, if you look it up, is 0.387, and for water it's 4.18. Remember, we said that metals have much lower specific heat capacities than water. Okay, water is much more thermally insensitive, has a much higher thermal inertia than metals do. The initial temperature of the copper ball, that's what we're trying to find. Okay, we're assuming that when we place that copper ball in the calorimeter, its temperature was the same as that of the Bunsen burner flame. So that's our big unknown in this experiment. The cold water, Theo measured its temperature to be 23.3 degrees Celsius. And the final temperature of the water, that is our equilibrium temperature after, okay, the water and the copper were at the same temperature, that is when thermal equilibrium was reached. Okay, that final temperature of both the copper ball and the water is 57.2 degrees Celsius. So now that we have conducted the experiment and we have our data, we are now ready to analyze the data, okay, perform the calculations in order to determine the temperature of that Bunsen burner flame. So remember, the calorimetry theory is based on the law of conservation of energy, simply that the amount of heat lost by the hot object will be exactly equal in magnitude, opposite in sign, to the amount of heat that is gained by the cold object. The hot object was our copper ball. The cold object was the water in the calorimeter. So we're assuming that there was no heat loss to the environment, okay, in our calorimeter. So here, okay, using our equation, the heat lost by the copper ball would be the mass of the copper, specific capacity of copper, times the change in temperature of the copper ball, and likewise for the water, okay, on the right-hand side of the equation. And remember, the negative sign comes from the fact that, Okay, the copper ball will end up at a lower temperature, so its delta T value will be negative, okay, whereas the object that is gaining the heat, in this case the water, will have a positive value of delta T. So in order to reflect the fact that each of these objects has different signs of delta T, we need that negative sign. Plugging in our numbers here from the previous slide, okay, filling in the data. Our only unknown is the temperature of the flame. That is really the initial temperature of the copper ball. And we do the number crunching, we solve this equation, and we find out that the flame temperature is 628 degrees Celsius. So you see, clearly you couldn't just go stick in a thermometer in a 628 degrees Celsius flame, okay, but using a calorimetry experiment, we can figure this out pretty easily. And I would say that, you know, the temperature of a Bunsen burner flame is variable. Certainly that when that flame is red, its temperature is going to be much less than this. But when it glows blue, you end up with that blue flame, its temperature is going to be somewhere between 600 and 700 degrees Celsius.